Hello everyone, this is Sharon from Learnacon and welcome back to another video on industrial automation. Today we will dive into a practical example to learn how to create a good estimate for a PLC programming job. As an automation specialist, mastering the skill of evaluating work and building precise estimates is essential for delivering successful projects. Let's see what we need to do. To build an accurate estimate, we first need to break down the project into quantifiable inputs. This summary is the foundation of our entire estimation process. It always starts with I/O count. First, we count the digital inputs and outputs. These are the simple on or off signals like start-stop buttons, limit switches, and indicator lights. For this project, we have a total of 80 DI/DO. Next are the analog inputs and outputs. These are variable signals that measure things like temperature, pressure, or flow. Analog points are typically more complex to program than digital ones. Here we have 40 analog I/O. Then we identify the number of PID loops. These are critical for automatically controlling a process variable like maintaining a set temperature. Each of these 5 loops requires significant programming and tuning time. If you need to learn more about PID loops, please watch my PID intro in the channel. Here is the link. We also have 4 variable frequency drives, which are used to control motor speed. Programming these involves setting up communication and creating logic for speed control and fault monitoring. If you need to learn more about VFDs, please watch the VFD video in my channel. Here is the link. In addition to VFDs, we have 10 standard on-off motors. While simpler, each one still needs its own logic for control and status feedback. Similarly, we have 10 automated open-close valves. Each requires logic to command its state and to verify its position using feedback signals. Finally, and most importantly, we define the major equipment sequences. This is the core logic that dictates how all the individual components work together to perform a process from start to finish, such as a CIP or clean-in-place skip. In this project, we have 2 main operational sequences to develop. Before we start translating our inputs into hours, it's critical to define our assumptions. These set the boundaries for our scope of work and ensure our estimate is accurate and fair. First, we are assuming the use of a regular PLC. This is a standard controller. It's not a safety PLC or a redundant system, both of which require significantly more programming, validation, and testing efforts. Then, we specify type of I/O modules we may use in this project. For example, 16-channel card for digital inputs and outputs, and 8-channel card for analog signals. Next, our estimate assumes that the PLC panel is already physically built and wired. This means our scope is focused purely on the software development and commissioning, not the electrical design or assembling hardware. We are also including the time for a loop I/O check. This is an essential commissioning step where we manually verify every single wire and terminal to ensure that they are correctly connected to the PLC inputs and outputs before we begin testing the logic. The loop I/O check means verifying the signal from PLC I/O channel all the way to the sensor or actuator. And finally, we are assuming there is no advanced motion control in this project. We are not controlling any high-speed servo drives or complex coordinated motion systems, which is a specialized and much more time-consuming area of automation programming. Okay, now I'm switching to my Excel file and going through the estimate. I've already put together an estimate and I'm going to explain what I did in every step. I've divided the estimation process in 2 categories. First, evaluating the work that requires to be done on the hardware system, and then going to the software side. Okay, so let's see what we have in the hardware. So you need to start with putting together PLC component. Based on the I/O count, we have only one PLC system. That means one rack, CPU, power supply, and I/O cards. Please keep in mind, both hardware and software configuration and programming are done in the PLC programming tool provided by the PLC vendor. So let's start with the hardware part. We have one PLC system including CPU, power supply, and I/O cards. You may need to spend like half an hour to put together all the required component in your software tool. And then you need to download this into your hardware and make sure it's running. Sometimes depends on the CPU, depends on the hardware. You may need to spend some time on updating firmware if needed. Next is digital I/O cards. So for every module, you need to define tag for every channel, and you may also need to set some simple parameters like voltage, filter, and other things. Typically, most PLCs these days allow you to copy-paste configuration from one channel or card to another one. That will speed up the configuration process. As we assume the panel has been already wired, we also need to check the connection from every channel to the terminal point that goes to the device inside the panel. So that's a simple continuity check. For every module, I consider like 15 minutes for configuration and half an hour for that kind of testing. So with 5 modules, we're going to end up to about 4 hours. Similarly, we have to repeat the same task for analog I/O cards. However, for analog channels, we may need to spend more time on configuration and testing. After that, we need to go through the complete loop I/O check. That means testing signals from the PLC channel all the way to the sensor or actuator. For a typical digital input, for example, you may press a push button at one side and then verify the signal is received inside the PLC on the other side. Just keep in mind, we still don't have any code loaded into the PLC. So this is a test that's done without the code. For every digital channel, I consider like 15 minutes to go through the whole test. You might be able to go faster or slower, or at some points you may find some wiring issues that you need to fix. So this is just an estimate that gives you an idea how much the whole thing may take time. So for 80 digital I/O, you may need like 20 hours to go through the whole thing. Typically in this process, you also need to have some documentation and record everything on a checklist. Okay, so that was the loop check for digital signals, and we need to repeat the same thing for the analog. The example for the analog side would be injecting a voltage through the PLC output channel and verify if the voltage is received on the actuator side. That's a summary of the efforts required for the hardware part. As you see, about 40 hours or a week is required to handle the hardware part of a PLC system with this amount of I/O. Okay, now let's shift the focus to the software part. In the software side, there are repetitive tasks and there are tasks you may do only once. In the software world, there are different methods to develop the code. I suggest to go from top to down. So it's better to start with creating a program structure and implement that using empty blocks. That would be done for the whole PLC system, and you might be able to do that in like 2 hours. Next, we need to go through each I/O points. So for every I/O, you need to write a code to handle that signal, either inputs or outputs. I consider the quarter hour for every digital point. And as you can see, the bulk of hours would be used here because you have to create a code and you also need to do the testing. Similarly, we have to repeat this task for analog signals. However, for analogs, we need to spend more time because we have to do scaling and descaling as well. And we deal with the range of signal, not just the simple binary on and off. Next is to estimate how much time is needed to create and develop the code for a sequence. In this project, we have 2 sequences, and for every sequence you can create a logic. And if the sequence is not too complicated, you might be able to create the logic in like 2 hours and spend like 1 hour for testing. After that is the PID loop. For each PID loop, we have to configure a function block, configure multiple settings, and set several parameters, which takes time. So considering 2 hours to configuring each PID loop is reasonable. Then we may need to spend same amount of time for testing and tuning. Next is the VFD. For VFDs, depends how they are connected to the PLC, either hardwired or over a communication network. We need to set a lot of parameters and configuration. So we can account 2 hours for configuring each VFD, and then the testing part would be fairly easy. Again, we assume that the drive and motor system has been already wired and powered up, so it's ready for testing. We learned that we also have 10 on-off motors in this project. For motor control, first we need to develop a function block based on the preferred logic desired for this project. That's a one-time thing. We may need to spend like 2 hours for creating the logic and 1 hour for testing. Then for each motor, we need to configure the function block, assign the tags, and adapt the parameters. So that's fairly easy. In the next section for the valves, we may need to repeat the similar process. So we create a function block for valve control and then create instance of that function block for each valve. Up to now, we covered maybe more than 80% of the required logic. Typically in every PLC program, you need to create a section to create and manage the alarm. Based on the provided functional spec by the client, you may need like half a day for creating the alarm and maybe 2 hours for testing them. Next is estimating the efforts required to create maintenance functions. For instance, for every fan, pump, or motor, the client may need to track how many hours it was running. So you may need to create a program to track that. And with that, you also need to take account time for testing and debugging. Next part is error handling. So what if a motor or valve function failed? How your PLC needs to react? You need to consider that in your logic. That is a very important part. You may need to ensure that your PLC program will never leave the system in an undesired, unknown status. You need to create a case for every possible scenario that may happen and ensure that the PLC is always in control. Last but not least is the overall interlocking part. So that's where you interface different functions and program blocks together and ensure that the whole program components work together as required. Okay, that's a summary of the main tasks you may need in the software side. Depends on the project, you may have more efforts or less. So you can tune that based on the given requirements. Next is the admin part. So a PLC project is not complete if you haven't done documentation. So you need to make sure to create description for every function block, to create tags, comments, and description for every I/O point, create a comprehensive table for the I/O list, cross-reference, and create a copy of the fully tested and functional program. So with that, we have 174 hours for the software development, coding, and documentation. Next is to sum up the required effort for the hardware and software part and add some contingency for unforeseen matters that typically happen during the project. Adding a 10-15% extra time is something typical. So in total, I've estimated 246 hours for this job. That's equal to 7 weeks of work, which makes sense. For a PLC job of this size, I always recommend to account for at least 2 months. You might be able to do it faster, let's say in a month, but you need to consider a lot of risks. Okay, with that, I would like to wrap up the topic, how to estimate a PLC programming job. I hope this video helps you to estimate your PLC applications with more confidence. If you learned something new, to support this channel, I appreciate if you subscribe, like, and share the videos. Thanks for watching and see you next time.